Hello everyone, and this is physics. In this video, I'd like to have a discussion regarding fluids, in particular compressible fluids, incompressible fluids, and then we'll finish the video with Pascal's Law. Now before I start, I want to talk about a special kind of fluid that really needs no introduction. So at this point, I would say, press the pause button, go and get your favorite drink, come back and enjoy the show on fluids. So speaking of compressible fluids, we're talking gases. I have here an enclosed system. In this is just air. Air is a gas. It comprises of nitrogen and oxygen. That would 79% nitrogen, 21% oxygen, thereabouts. And there's nothing in here except air. And I bought 2 syringes. Speaking of buying these 2 syringes, when I had this idea, and I know many others have had a similar idea or the same idea, I'm certainly not the only one who had this idea, but when I did have this idea, and I said to myself, I need to go and get some syringes. In order to do so, I thought, where could I buy syringes? A pharmacy. So I went to a pharmacy and I approached the counter and I was talking to the clerk and I mentioned to her, I need to buy some syringes. Whoa. The clerk stepped back, called the pharmacist over and says, look. And then I had to explain to the pharmacist why I was looking for syringes. And I say kudos to the gentleman. So, and I did my explanation and he believed me. And I have now these syringes and some others that I'm going to show you in a few minutes. And I say kudos to that pharmacist and the pharmacy in general for upholding their protocols regarding such items. Anyways, here I am, and I have these 2 syringes, and inside here is air. And if I take one apart, you see there's just air. We're under air pressure, so there's air inside here, air inside the syringe. And air is a gas, and we're talking now compressible fluids. And let's see what happens. Within this closed system, and I talked about the word system some videos ago, if I look at an enclosed system, such that there's no air coming in here, there's no air leaking out at the other end, and there's no air coming in or leaking out within the tube itself either. So this is an enclosed system. If I push down on this plunger, I expect to see a response on the other plunger. And let's do that. So I'm going to push down on this plunger. By the way, these are both 10 milliliter plungers. They're identical plungers, 10 milliliters each. If I push down on here, I expect to see a response on the other side. I'm just looking here at the plunger, see, or you can look down here, see if it moves any as I push down. And you'll notice I'm pushing down, but there is no response on the other side. Well, what's happening here is I'm basically squeezing all the air molecules together. Air, nitrogen, the oxygen, they're far apart. And as I apply a force at this plunger right here, all I'm doing is squeezing the air molecules back together again, or closer together again, I should say, closer together, and not getting a response on the other plunger until I reach a point which that the molecules have finally compressed enough in order to give me a response. So I'm pushing down, and now I'm getting a very small, slight response on the other side as I push down. Because I'm pushing on my right, pushing down, and slowly there's a response on the other side. This is as the molecules are getting compressed. Hence the word compressible fluids. And if I push all the way down here, the response is not complete on the other side. I started with 10 milliliters at this end, and I'm finishing with just a little over 8 milliliters on that end where the plunger is. So some of that work is being used in order to compress the gases. If I go the other way, a similar thing will happen. I'll push down and there will be no response here. And as I continue to do this, eventually I'm going to compress all the gases and then to start getting something. And the same thing will happen here. I'm pushing down and there's no response on the other side as I just squeeze the atoms. This is known as compressible fluid, and it basically applies to gases. There is another name for this in the world of industry. They call that pneumatics. Basically compressing gases in order to do work in industry. It's known as pneumatics, and we're simply going to call this compressible fluids. In the world of incompressible fluids, well, those are liquids. I have here another system which I put together. In it is water, green water. I added some food coloring in order to so you can see this. And I have two different size plungers. I have a small one here. This is 10 milliliter plunger, and a larger one on the other side. And this one is a 20 milliliter plunger. And I'll talk about these different sizes in a few minutes. But I also made a note in order to leave an air bubble in here. You will see the air bubble. I'm just going to move the air bubble over to the other side if I can. Nope. Okay. And just okay. So I'm back to compressible fluids. In here I have liquid. Liquid is an incompressible fluid, and inside of it there's an air bubble, and that air is a compressible fluid. So in order to do another demonstration of a compressible fluid, see if you can see this, I am going to squeeze with my left hand right here, and let's see what happens to the actual air bubble as I squeeze with my left hand. Try and put this here. I'm squeezing now. You'll notice the air bubble is getting smaller. As I squeeze, the air bubble itself getting smaller. Now I'm trying to hold it in place here so it doesn't really move. And that is a compressible fluid. Now having an air bubble within a incompressible fluid, or within this liquid right here, could be a very bad thing. If you consider the circulatory system of the body, we have incompressible fluid called, well, blood. And if we happen by some chance get an air bubble in our blood system, our circulatory system, and that air bubble eventually gets to the heart, well, you wind up with a heart attack. So having air in our circulatory system would be a very bad thing. Also, this is what is used for brakes. Yeah, I'm getting a little ahead of myself, but nonetheless, this is the same what that happens in the brake systems in a car. It is an incompressible fluid. Should there be air in the lines of a brake system, your brakes in your car, when you step on the gas pedal, what happens? Well, your pedal is going to go down to the floor, because the first thing you're doing is compressing the air. So you want no air whatsoever within your brake system in your car. And the brakes operate on incompressible fluids, such as this one right here, incompressible fluids. Now, let's have a look at incompressible fluids themselves. I'm just backtracking a little bit. Again, in here I have water, and I've colored it. Okay? Now, incompressible fluids are liquids, water, oil. Okay? And I'm going to move that air bubble out of the way. I'm going to try and put it into one of the plungers. Let's put it into this large plunger right here. I'm going to try and squeeze that air bubble and get it out of the way. It's still within the system. You can see it floating up. There it goes. So now the air bubble is up here at the very top. I just have to ignore the fact that I do have some compressible fluid here, and we'll just assume that this system right here is filled with water, which is an incompressible fluid. And now imagine the whole thing is incompressible. Here it is. And this is an enclosed system again. There's no leaking here, no leaking on that side. I know there's no leaking on these guys because I put crazy glue here and I put crazy glue there just to make sure there's no leaking. And now as I squeeze this, and now I'm talking incompressible fluids, and I have to ignore that little bit of air which I left in here in order to do the demonstration, just ignore that little bit. As I push down on the plunger now, I'm going to reset this and go the other way. I'm going to put this as much like bring this plunger up to the other side. Here we go. You'll notice that as I push down, there is an immediate response on the other side, ignoring a little bit of air. So now that I have this basically set, I have a small plunger on my left and a large plunger on my right. And of course I connected with the hose. And this is an incompressible fluid, water, oil, any other liquid. And as I push down on this plunger, the one on my left, you will notice that there is an immediate response on the right. Here we go. Now I need to go down a fair bit in order to get a response on the right. It has nothing to do with that air, it has to do with the size of the cylinder. that is a topic for another story, or another video, I should say. But what happens here when I have an incompressible fluid is I push down on one, there is immediate response on the other. And I'll go the other way around. So I push down on here. I'm going down, and there is an immediate response on the other side. So I'm applying a force down here, and what's happening on the other side is the force is going upward or going the other way. And this, again, as I said earlier, is how your brake system works. Your brake system, it has a master cylinder on one side. It's got slave cylinders on the other side, or some today they use rotors. No, calipers, my mistake. They use calipers. Okay, it still has a slave cylinder in it. And this is how your brake systems would work. You would push down here on with your foot on your brake, and there is an immediate response on the other side. And you already know this, those of you that drive. As soon as you touch your brakes, your car comes to a stop. And that's because it is an incompressible fluid. If there was air in your brake lines, your brake pedal would go to the floor, and that would be a very bad thing. It means you have a leak somewhere. That would be very, very, very bad. And that is an incompressible fluid. Now, incompressible fluids in the world of industry also have another name. We have pneumatics for compressible fluids. This also has another name in the world of industry called hydraulics. And that's just a little added information. We're most interested in these two right now: compressible fluids, which are gases, incompressible fluids, which are liquids, and the effect is immediate. Now let's look at Pascal's law. I'm going to do Pascal's law and use this as the example for Pascal's law. I'm going to draw a sketch regarding these two cylinders and the connection in between them. And there is going to be a liquid. Typically, when we're doing Pascal's law in the variety of textbooks, the ones that you've seen here behind this board and many others, it's drawn this way. We have a small plunger at one side. I'm just going to draw a plunger here. And here's the cylinder. There's the plunger. And we need an enclosed system. This will represent the tube. And at the other side is a much larger plunger, or a much larger vessel. And we're going to keep them at the same height. And of course, the tube needs to extend in order for the plunger to go up. And there it is. We're going to do Pascal's law, looking at this system right here, and that represents what I have here. I have a small cylinder at one end and a large one at the other end. If I were to apply a force here on the left, I'm pushing down on the plunger, much like you saw me do. I'm going to call this force F1, pushing down. And this has an area, this plunger, and it's circular. So the area here, as you can see, is the circle. So the area will be pi r squared, but it has an area nonetheless. It could be rectangular or any other shape, but it has an area. I'm going to call this A1. Now the formula for pressure is force divided by area. Therefore, our pressure is going to be developed right here inside this system. This is a closed system, and there's a fluid in here. In our case, it's water. The pressure is going to develop in here. I'm going to call that pressure at 1 is equal to force 1 divided by area at 1 here on the left. Over here on the other side, if I were to do the same thing, now this might get a little bit confusing, but it's a development of the equation here for Pascal's law. I have a force. If I'm pushing down here, obviously the plunger is going to go up. So I'm going to call a force here, force 2, and it's going up. I won't show the arrow, but there's a force 2 that is going to be generated here at this end as a result of this one. There's also an area here for the plunger. And as you can see, the plunger has a larger area than the other one. So I'm going to call this area A2. Call the area of that plunger A2. Therefore, the pressure that's being developed here is same equation, except for the subscripts. I'm going to call it pressure at 2 is equal to F2 divided by A2. That's over here. Now, Pascal's law states Let's have a look here at Pascal's law. It states Pascal's law. I'll show this to you in a minute. Pascal's law states that a pressure applied to an enclosed fluid is transmitted undiminished to every portion of the fluid and the wall of the containing vessel. Here it is. Pascal's law states that a pressure applied to an enclosed fluid, and I'm going to apply a pressure here. To an enclosed fluid, it's completely closed, there's no leaks. The enclosed fluid, the pressure is transmitted undiminished. Therefore, the pressure here, P1, is transmitted undiminished throughout this system. And that means it's going to have applied pressure towards the wall on the outside, and it's going to apply pressure on the outside wall going down. It's going to apply pressure to the right and apply a pressure going to the left. So the pressure is everywhere. The fluid is transmitted undiminished to every portion of the fluid, and the containing vessel. So pressure is down here. That'd be P1 down here. P1 pushing up, P1 pushing down, P1 pushing to the right. Going up here. Then we're going to have P1 pushing up on that plunger. But we already calculated now that the pressure here should be pressure at 2 is F2 over A2. But pressure at 2, however, is exactly the same as P1. So what's happening up here? Pressure at 2, according to this equation right here, and since the pressure is the same throughout this system, P1 and P2 are equal. I'm going to drop this down a little bit. At this point here, pressure at 2, or pressure at 1, generated here going through the system is equal to pressure at 2, mathematically calculated at the other end, is equal to pressure at 2. This is the left-hand side of these two equations. If I were to equate the right-hand side of these two equations, F1 over A1 must then be equal to F2 over A2. Let's drop this down a little bit. The left-hand side of P1 is F1 over A1, then must be equal to P2, which is F2 divided by A2. Mathematically, this is known as Pascal's law. Mathematically. Okay. And I'll read that again. Pascal's law states that a pressure applied to an enclosed system, so no leaks, okay, is transmitted undiminished to every portion of the fluid and the wall of the containing vessel. And with that, okay, this is physics.